Yeah, now moving on from the multi-layer networks, like the multi-layer perceptrons, to deep learning. So we are going to talk about the origins of deep learning in this video. So coincidentally, I just submitted a paper today with collaborators where we used multi-layer perceptrons, and we were debating whether we should call it deep learning or whether we should avoid the word. The reason is deep learning is a relatively new word, like that was invented, I would say, like 10, 15 years ago. But multi-layer perceptrons have been around for at least like 30, 40 years, right? Like I talked about in the previous video. So is this really deep learning? So yeah, that is kind of debatable. So technically, when the term deep learning first occurred, when it was first used, what people referred to was the representation learning with advanced architectures with many layers. So having multiple layers is not really what makes the difference between a multi-layer perceptron and deep learning. It's more like the representation learning capabilities. That is usually what deep learning is all about. So nowadays, though, if you read papers, newer papers where people use multi-layer perceptrons, they call them deep learning too. So I think nowadays it's okay to also call it deep learning to make it maybe less confusing for people, because everything nowadays that is a neural network is also automatically deep learning. But let's dive a little bit more into the representation learning aspects that I just mentioned. So that goes back to also the approximately 1990s. So also in that way, it's a thing that was discovered or invented before deep learning was a thing, the word deep learning, and that is convolutional neural networks. So this is kind of on top of the multi-layer perceptrons. It's like, you can think of it as a specialized version where you have locality. So here it's about making training more efficient and also extracting local features, which then better capture feature dependency. So recall in multi-layer perceptrons we had like the feature independence, so it would work with tabular data. Now with this convolutional network we can leverage some prior knowledge or this relational inductive bias. So it's specifically for image recognition, for image data. So how a multi-layer perceptron works is you have these independent features, and the convolutional network captures dependency. On the right hand side I'm showing you this original LeNet architecture from Jan LeCun and co-workers that was applied to handwritten zip code recognition. And we will have a dedicated lecture just to convolutional networks later, but here just a brief overview is that it consists of two parts. So there's one part that is the convolutional part. So here you have convolutional layers. They have a trick or a concept called weight sharing, and there's also pooling involved, and that makes the training more efficient. We will discuss this in more detail later, but you can think of it roughly as the feature learning layers, where these layers are able to extract abstract features from the data, and these features are then passed on to a fully connected set of layers. So these are fully connected layers, and these are essentially a multi-layer perceptron, and you can think of it as a classifier here. So if you think of it as a task, let me also use red here. So here we have this part, the lower part here, for feature learning. This upper part is for classifying the features that have been extracted by these earlier layers. So this is making the handcrafting of the features obsolete. Now the network learns the features, and it learns it in a way such that it is optimal for the classifier, because everything here is connected, so it's learning together, which is one advantage that makes neural networks for image data specifically very efficient. So this is from the 1990s. Back then the term deep learning didn't exist, but I would say nowadays convolutional neural networks are really like the most popular form of deep learning, because there are, many advances that followed this earlier architectures and made deep learning what it is nowadays. Of course, there's also a separate branch of recurrent neural networks that is also very popular in deep learning. So recurrent neural networks also are, I would say, an advanced version of the multi-layer perceptron. So here, what's new is that there is a recurrence. So you can think of this as a multi-layer perceptron, but a multi-layer perceptron is a feed-forward network. Now you have this recurrence, so you are revisiting earlier things. So again, this will be covered in way more detail in a dedicated lecture later on in this course. But the key idea is basically that we have a modified version of backpropagation, which is called backpropagation through time, because there's a time component. And this is especially useful for sequence data, where there's a sequential dependency in the data across the features. So, but the problem with that is now when we train neural networks with many layers, especially if a recurrence over a long sequence, there's this problem of vanishing and exploding gradients. So that is like a big challenge. However, it was also, there are many potential solutions to that. One of them that is, one of the ones that is still commonly used is LSTMs. That stands for long short-term memory. So also this one was overcome. And this is also one popular form of deep learning, like using these neural networks. But again, this is something that has been around for a long time. Actually, I don't know exactly when recurrent neural networks were invented first. It was also in the 1980s, sometime after backpropagation was invented, because this is an advancement of backpropagation. It was sometime in the 1980s. Just to summarize what originally the term deep learning meant, here's a nice section or sentence from the deep learning review by LeCun, Benjo, and Hinton. So Hinton was the person working on the backpropagation algorithm. LeCun was the one who came up with the convolutional neural network. And Benjo is doing a lot of work also across deep learning, mainly also focusing on the recurrent neural networks, but also basically everything. So in this review, the sentence goes like this: representation learning is a set of methods that allows a machine to be fed with raw data and to automatically discover the representations needed for detection or classification. Deep learning methods are representation learning methods with multiple levels of representation. You can also say abstraction. And so here the focus is really the implicit feature extraction that deep learning does. That is something that traditional machine learning is not capable of, like we talked about last week, where we have the handcrafted features versus the automatic feature extraction. So here the focus is really on the automatic part. But nowadays, really, deep learning means the same as using neural networks. So deep learning nowadays, it's really the same as using neural networks. Maybe we should be a little bit more specific and say multi-layer. But going from these architectures I showed you that were invented in the 90s towards the modern era of deep learning research, there was unfortunately in between another AI winter in the late 1990s and early 2000s. And I think that was probably due to the popularity of support vector machines and random forests. Because back then, neural networks were capable, but they were very expensive to train. So you needed enormous computer hardware to train them efficiently, and even then you had to wait a long time to train them. So they were not easy to train compared to, let's say, support vector machines and random forests. Of course, support vector machines come with their own set of problems, like the really inefficiency of RBF kernel machines on high-dimensional data. Also, random forests require a lot of trees. But still, compared to deep neural networks, these were easier to train and worked quite well. But then at some point people figured out how to use GPUs to make the training of neural networks more efficient, and that is really what helped making neural networks really popular and feasible. So when I looked at literature, what I could find, it goes already back to 2004. So GPU implementations of neural networks have been around for quite some time, but really when it became popular was in 2012, where Krzyzewski, Sutskever, and Hinton worked on ImageNet classification. It's a very common benchmark data set, like millions of images, where they used deep neural networks trained on GPUs to outperform traditional computer vision approaches. So a few more words about that in the next couple of slides. So here's a table from my 2017 book. I actually updated this last year, so I don't know why I have the old one here. Maybe I should swap it. But again, so the bottom line here is more that the difference between traditional CPU, for example here an Intel CPU, and an NVIDIA graphics card, or in general a graphics card. Maybe think of it as the difference between a CPU and a GPU. And GPUs are particularly good at linear algebra operations like vector and matrix operations. So even though GPUs have a smaller clock frequency, one advantage is really like the parallel cores. Each core is slower than a CPU core, of course, but you have more of them, and that helps you parallelizing computation. So parallel computing of dot products and matrix multiplications is really what makes GPUs very useful for deep learning. So you really get a way higher memory bandwidth also. So the GPU memory, GPUs come with their own memory, which is closer to where things are computed, so it's also faster. In that way, if you have the data on the GPU, however, you have to get the data to the GPU, which is sometimes a little bit slow. So there are some tricks also to make this efficient in terms of data loading. But this is something we will talk about when we actually use PyTorch for deep learning. I will also show you how you can use GPUs. For this class, you won't need a GPU. I will later on talk about some free online resources where you can get one GPU for free, which can help with some homeworks and also the project. But you don't need to buy your own GPU or something like that. And moving on, so really you can see the number of floating point calculation. A float is, you can think of it as a decimal number in the computer. You can see it has a way higher number of floating point calculations. And it's also cheaper, at least compared to this high-end Intel CPU. But of course, there are also things with GPUs that make certain things inconvenient because they have their own memory, which is not very large. I mean, there are nowadays more expensive cards that have larger memory, but usually in deep learning, GPU memory is the bottleneck, at least for me. But again, that is a topic for another day. So here's another fun quote from the Architects of Intelligence, like an interview with Geoff Hinton. So it is about when... so regarding the question, when did deep learning become really popular? So here again is a fun quote one excerpt from interview from the book Architects of Intelligence. And this refers to the 2012 ImageNet competition. So there was a famous computer vision competition on a dataset called ImageNet. And it was essentially about a benchmark, and people submitted, computer vision methods and papers, and it was about having the best system each year who could do the best classification on this image dataset. It's like a image dataset consisting of up to 14 million images. They used only a subset at that time, as far as I remember, but it was millions of images. And back then, really, the conferences were dominated by traditional computer vision approaches like manual feature engineering and so forth. No deep learning, really. And here in this interview, I don't want to read everything here. Maybe you can pause the video and read through it if you are curious. But it is essentially about that deep learning methods were usually rejected. So here's like something I underlined. The referees thought that it was the The referees thought it was the wrong way to do things, referring to the neural network architectures here. So people really didn't like deep neural networks back then. I mean, people who were using traditional computer vision systems. However, the network that was submitted that year in 2012, the AlexNet, which was by Alex Krizhevsky, Sutskever, and Geoff Hinton, was really outperforming traditional computer vision methods by a large margin. So they achieved a 15.4% error in 2012 on top 5 classification. I will, in the next slide, explain what top 5 accuracy or error means. So forget about top 5 for now. So they achieved a 15.4% classification error. And the second best method only achieved 26.2% error. So their method was about twice as good as any traditional computer vision system. By the way, as a side note, nowadays you can even get down to 3% error on ImageNet. So even like since 2012, things improved quite a lot. But yeah, so just briefly here, the last thing. So people were really surprised about how well deep learning worked, and then also, like he says, within 2 years they all switched. So for things like object classification, nobody would dream of trying to do it without using a neural network now. So this was really like 2012 was really like the breakthrough moment for deep learning, because yeah, it performed really well on image classification. Yeah, and here's also just a quick overview of the benchmark datasets. Nowadays there are other even bigger datasets, but these are still common datasets when you develop convolutional networks or object classification methods. So there's the traditional MNIST dataset from 1998. 60,000 examples, 10 classes, and very low resolution images. So these are the handwritten digits. So this is still a great data set for debugging your neural network. It's like when you want to try a network, get the code written and see whether it works, because it's really fast to train a network on that. In practice, if you write a conference paper, testing your method on MNIST may not be enough anymore. But yeah, it's still a good way to start. A more, I would say, advanced dataset is CIFAR 10 and CIFAR 100. So there are 60,000 examples of either 10 classes, which is for CIFAR 10, or 100 classes in CIFAR 100. Again, very low resolution, 32 by 32. Now though we have color images, so we have 3 color channels. And yeah, we have different objects here to classify. There's usually only one object in each image. A more challenging dataset is the ImageNet dataset, which consists of 14 million images. So they have full resolution, and but what is a little bit more challenging about that too is that there can be multiple objects in an image. I talked about in the stuff in the news section where people were relabeling ImageNet, but yeah, so what can happen is that there could be multiple objects sometimes, so or it can be kind of ambiguous. So usually what people do is they measure the top 5 accuracy or error. So for example, when you have a prediction, you check whether it's so whether your top 5 labels are matching with the image label, because a network is trained to return a probability or a confidence score for each possible class, and then you look at the top 5 most confident labels, and you look whether one of the 5 labels matches with the label in the image. For example, it's a little bit small, I can't really read this here. Let me see. But let me pick an example. So here, for example, we have actually also 2 things. We have a cherry and a dog. So it's also, you can see this is like a challenging example where your network may predict dog, but since the data point here is labeled with cherry, it would actually count as an error, which is kind of unfortunate. So you would look whether your prediction is kind of within the top 5. Or here in this case, your algorithm may predict car or grill, like the grill of a car. Both would be correct, right? So in that way, you look is whether grill is under your top 5, for example. So in that way, it's a little bit harder to evaluate on ImageNet compared to CIFAR 10. I think in CIFAR 10 it's a little bit more obvious. Not more obvious, but here you have classes where it's at least a little bit less ambiguous. All right, but yeah, moving on. I don't want to make this brief overview lecture like too long, because we will dive into these little concepts in way more detail later throughout this course. So like a last thing here, of course, there have been many advances since 2012. So, okay, this is 2010, but for example, advances that are making deep neural networks work way better. So common ones or popular ones are ReLU units, rectified linear units, which are activation functions, very simple but very effective. Batch normalization, dropout, generative adversarial networks, and these are all covered in this course and many more. So there have been a lot of advances also in the last decade, and these are already like 6-7 years old, and so there are way more of these, and they are all contributing together to make deep learning work better. So in the next video, I want to very briefly talk a little bit about hardware and software landscape, what has changed in the last few years, and then briefly going over some current research trends, and then really wrapping up these series of videos here for lecture 2, and then that we can go into our more detailed lesson on perceptrons.